Right now, someone is selling land on the planet Kepler 452b for $29.99 per acre. A planet that is 1,810 light years away from us, meaning light from it takes 1,810 years to reach Earth. But here's the crazy part. We're not even sure it exists. And this isn't an isolated case. The media has told you we found Earth too, planets with life, places humans could migrate to. Let me give you the real numbers. 6,000 exoplanets have been discovered. 27 of them are called potentially habitable. Sounds impressive, right? But the truth? There might only be 3 worth our attention. So what's the problem? Why aren't most of these planets what we think they are? There are 3 core issues the media never tells you about. Problem number 1. Red dwarf stars. 70% of stars in the universe are red dwarfs. Sounds great. More stars means more potential planets, right? Wrong. Red dwarfs emit extremely powerful ultraviolet radiation and X-rays, constantly flaring with bursts of energy. These flares aren't like gentle sunlight streaming through your window in the morning. They're like energy storms that can strip away a planet's atmosphere within a few million years. Imagine trying to hold a blanket in a tornado. That's what's happening to these planets' atmospheres. Problem number 2. Tidal locking. Most planets in the habitable zone of red dwarfs are tidally locked. One side always faces the star, one side always faces away. One side is eternal day, hotter than the Sahara Desert. The other side is eternal night, colder than Antarctica. But this isn't as simple as you think. Wait until I tell you about the TRAPPIST-1 system. These planets can escape from tidal locking and create an unimaginably chaotic environment. Problem number 3. Severe lack of data. For most of these planets, we only know the radius, just how big they are. We don't know mass, we don't know density, we don't know what they're made of. Rock? Water? Gas? We're just guessing. And there's a concept called the cosmic shoreline, where below a certain size, a planet cannot retain a thick atmosphere. If a planet is smaller than this boundary and orbits a red dwarf, it's basically dead from the start. So now, let me walk you through each planet one by one. And I promise you, the truth will be far more shocking than any headline you've ever read. Let's start with our nearest neighbor, Proxima Centauri b, just 4.2 light years away from us. In cosmic terms, this is like the neighbor next door. Proxima Centauri is one of the most active red dwarfs we know. It constantly spews out energy flares. Not once a year, not once a month, but every few days. These flares are so powerful they can double the star's brightness in minutes. Now, imagine you're living on Proxima b. You wake up on a normal morning, and suddenly, your sun becomes twice as bright and starts bombarding you with ultraviolet radiation. This is not an environment for life, but it's worse than that. Recent models suggest Proxima b may have formed too close to its star when it was young. This means the planet could have been heated enough to lose all its water, if it ever had water. This is probably just a dry rock with no atmosphere, bathed in deadly radiation every few days. Next is GJ 1061c and d. These are 2 slightly more interesting planets. They lie in what's called the habitable zone, and some scientists have suggested they might have liquid water oceans beneath a thick layer of ice, similar to Jupiter's moon Europa. Sounds intriguing, right? A hidden ocean world. But here's the problem. We have no actual evidence for this. This is pure speculation based on models. And honestly, if they're like Europa, they're still not ideal environments for complex life. Europa might have an ocean, but it's a dark, cold ocean, isolated from the sun by tens of kilometers of ice. And most likely, GJ 1061c and d might not even have any atmosphere at all. Now we come to a truly alarming case. Gliese 667 cc. This is where things get serious. There's a research paper about this planet with a very memorable title, Death by Fire. And that title is not an exaggeration. Gliese 667 cc has a unique problem. It sits in a triple star system with at least 2 other planets nearby. These planets create extremely strong tidal forces on Gliese 667 cc, and its orbital eccentricity, basically how elliptical its orbit is, oscillates from 0.05 to 0.25 in just 6 Earth months. What does that mean? It means the tidal forces on this planet are constantly changing, wildly. Imagine you're living on Gliese 667 cc. For 6 months, your planet is being stretched and compressed by changing gravity. The planet's interior starts heating up from friction, temperature rises gradually, and then volcanoes start erupting. Not just a few volcanoes, but global volcanic activity. The surface melts. The atmosphere is blown away by continuous eruptions. This is not a habitable planet. This is a super Venus, a volcanic hell where surface temperatures could exceed 500 degrees Celsius. Now, let's talk about the TRAPPIST-1 system. This is probably the most celebrated planetary system of the past decade. But here's what few people know. TRAPPIST-1 has a huge advantage over most other planetary systems. We know both the mass and radius of these planets. This is extremely rare, and more importantly, the James Webb Space Telescope has actually observed them. We have real data, not just models. So, what does James Webb say? 95% chance it doesn't have a thick atmosphere. This is the first time in history we've eliminated a planet from the potentially habitable list through actual observation, not just theory. TRAPPIST-1d is officially out of the game. But what about TRAPPIST-1e? This is the planet considered the most Earth-like in the system. Data from James Webb shows 2 possible scenarios. Scenario 1. No atmosphere. Just like TRAPPIST-1d, this fits with the cosmic shoreline theory I mentioned earlier. Scenario 2. It has a nitrogen-rich atmosphere, like Earth. Sounds promising, right? But there's a big problem. The signal from the atmosphere might just be noise from the star. TRAPPIST-1, like all red dwarfs, has a lot of surface activity. Star spots, energy flares. These create stellar noise that can distort our data. So we need much more observation. But honestly, most likely TRAPPIST-1e also has no atmosphere. Imagine this. You're living on TRAPPIST-1e. For 1,000 years, everything is stable. One side of the planet is always daytime. The other side is always nighttime. Your civilization has adapted to this. You build cities in the twilight zone, the Terminator zone, where it's not too hot, not too cold, and then, one day, the planets align. Tidal forces cross each other, and your planet starts rotating. Not slow, balanced rotation like Earth, but chaotic rotation. The sun starts moving across the sky. The zone that was eternal day now has night. The zone that was eternal night now has day. Ocean currents, formed over millions of years based on the old temperature pattern, suddenly collapse. Temperature fluctuates plus or minus 50 degrees Celsius in a few years. If there's any life, it will be wiped out. And then, after a few hundred years of chaos, the planet locks again, but in a completely different position. A completely new climate map. Everything has to start over. This is not a stable planet. This is an unpredictable, chaotic environment. There's no way complex life could exist here. Now we come to the planet that gave me the most hope, until I understood it more deeply. LHS 1100 140b. In early 2024, James Webb observed LHS 1140b. And the results? Fantastic. This planet has an atmosphere. It's not a mini Neptune, a giant gas ball like a miniature Neptune. It has low density, which means it contains a lot of water. And its atmosphere? Nitrogen, carbon dioxide, and water vapor, like Earth. When these results were published, I was very excited. This could be it. A real ocean planet. A place that could have life. Imagine. A world covered by blue oceans, with blue skies, with white clouds. A beautiful planet out there, just 40 light years away. But then, I read the more detailed research papers, and I discovered a problem. An extremely serious problem. LHS 1140b has too much water. Sounds strange, right? How can a planet have too much water? On Earth, our deepest ocean, the Mariana Trench, is about 11 kilometers deep. That's our limit. But on LHS 1140b, with the amount of water it has and its gravity, the ocean could be deeper than 1,000 kilometers. At that depth, pressure becomes extremely high. And under that pressure, something strange happens. Water is no longer water. It transforms into a special type of ice called Ice 7. This ice is not like normal ice. It exists at temperatures above 100 degrees Celsius. It's harder than steel, and it forms a solid layer at the ocean bottom. So what's the problem? The problem is Ice 7 blocks everything. Heat from the planet's core cannot escape. Minerals from the core cannot rise to the ocean. And this means no hydrothermal vents. On Earth, hydrothermal vents are where many scientists believe life may have begun. They're where hot water from the Earth's interior spouts out, carrying minerals, creating the perfect environment for complex chemical reactions. But on LHS 1140b, no hydrothermal vents, just a flat, cold sheet of ice at the ocean bottom. So imagine you come to LHS 1140b. You look from space. It's beautiful. A blue planet. You land. The ocean stretches endlessly. You dive down. 100 meters. Nothing. 1 kilometer. Still nothing. 10 kilometers. Still nothing. 100 kilometers. Just water. You keep diving. 500 kilometers. No fish. No seaweed. Nothing. Just water. Water. And endless water. In complete darkness. James Webb detected a molecule called dimethyl sulfide, DMS, in K218b's atmosphere. On Earth, DMS is only produced by life, specifically by marine algae. So if K218b has DMS, it must have life, right? Wrong. Let me explain why things aren't that simple. First, DMS was not detected on K218b. It was faintly suggested. James Webb's data could fit a model with DMS, but it also fits a model without DMS. The signal is too weak to be certain. Second, even on Earth, DMS doesn't always come from life. Some recent studies show DMS can be produced by chemical reactions unrelated to living organisms. Third, if life were truly producing DMS on K218b, we would see other molecules too. Specifically, we would see ethane. But we don't see ethane. This contradicts the life hypothesis. But the bigger problem with K218b isn't about DMS. The problem is its atmosphere is obscured by something called sulfur haze. And here's the weird part. This haze appears both above and below the cloud deck. And when we look at K218b's overall density and composition, it has too much hydrogen. This suggests it's most likely a mini Neptune, a gas ball with a thick hydrogen atmosphere, no solid surface, no ocean. So, my final verdict on K218b? This is a dry mini Neptune, no life. The media took an uncertain signal about DMS and turned it into a story about aliens. Now, let me introduce you to a concept that might completely change how you think about ocean planets. It's called Soot planets. Here's what most people don't know. When a planet forms with a lot of water, it also forms with a lot of carbon. The ratio is roughly for every 1 kilogram of water, you get 0.3 to 0.5 kilograms of carbon. This carbon doesn't disappear. It's there, mixed with the water. On a soot planet, the sky isn't blue. It's orange-brown, saturated with methane. The clouds aren't white. They're black as soot. And the ocean? The ocean isn't turquoise blue. It's black as ink, full of suspended carbon particles. Imagine you're standing on the shore of a soot planet. You look up at the sky. It's a gloomy brown. You look out at the ocean. It's completely black. You can't see through even a meter. And then it starts snowing. But that's not soft white snow. That's soot, black carbon particles falling from the sky, covering everything with a layer of black dust. And at the ocean bottom, under extreme pressure, carbon starts crystallizing. The seafloor of a soot planet could be made of diamond, not beautiful transparent diamond, but layers of compressed black carbon, stretching for kilometers. This isn't science fiction. We have real evidence. TOI 270d, a planet once considered an ocean planet, was observed by James Webb. The result? Methane and carbon dioxide. No signs of water. TOI 270d is a soot planet. And now, let me tell you about one of the strangest phenomena I've ever studied. A phenomenon I call the heartbeat day. Ross 128b has an orbit with fairly high eccentricity, 0.21. At the same time, it's also tidally locked with a 1-to-1 ratio, 1 rotation per 1 orbit. When you combine these two things, something strange happens. On most of the planet's surface, things remain normal. One side is always day, one side is always night. But in the terminator zone, the twilight zone between the two sides, the sun doesn't stay still at the horizon. It bounces up and down over 10 Earth days, roughly how long Ross 128b takes to complete 1 rotation. If you stand in the terminator zone, you'll see the sun at the horizon. Then, for a few days, it rises about 5 degrees above the horizon, and then it drops back down to the horizon, up, down, like a heartbeat. The consequence of this? In the terminator zone, ice melts and freezes continuously. Temperature fluctuates every few days. If any life tries to exist here, it would have to deal with an extremely unstable environment. Plants can't optimize photosynthesis because the sun constantly changes position. Animals can't maintain stable biological rhythms. And like many other planets we've discussed, Ross 128b might not have an atmosphere or might be a mini Neptune. We don't have enough data to be certain, but even in the best case, this is an extremely strange and unstable environment. And finally, let's talk about the Kepler planets. This might be the most controversial part of this video, but it needs to be said. Kepler 186f, Kepler 22b, Kepler 62e, Kepler 62f, you may have heard these names. They were once the bright stars of the potentially habitable planets list. Kepler 186f was especially praised as having a 99% chance of existing. But here's the problem. That probability has now dropped to 80%. And for most other Kepler planets, we only know the radius. We don't know the mass. We don't know what they're made of. They could be rocky planets, or they could be mini Neptunes. We simply don't know. So are there any Kepler planets worth noting? There are 3 I would say are still strong candidates. Kepler 442b. This is the strongest candidate among the Kepler planets. It has the right size, sits properly in the habitable zone, and models suggest it could have stable conditions. Kepler 186f. If it exists, it's very promising. It orbits a K-type star, not an extreme red dwarf, so it might not be tidally locked and could have a more stable environment. And TOI 700d, a relatively newly discovered planet, orbiting a very quiet, less active red dwarf. From 27 potentially habitable planets, we've gone through each one. And here's what we actually have. 9 planets are rocks, with no atmosphere, stripped bare by radiation from their red dwarfs. Nothing but barren rocks orbiting violent stars. 5 planets are mini Neptunes, giant gas balls with no solid surface, nowhere for life to gain a foothold. 3 planets are super Venuses, FA, volcanic hells where surfaces melt in fierce geological activity. 1 water planet, LHS 1140b, beautiful from space, but a dead ocean, lacking the chemical cycles necessary for life. 4 planets in the gray zone, we simply don't know enough to say. 1 planet with a thin atmosphere that may not be enough to protect any potential life. 1 Europa-like planet, if it's truly like Europa, that's a frozen ocean, isolated from sunlight. And then 3 real candidates. TOI 700d, orbiting a quiet red dwarf, potentially capable of maintaining a stable atmosphere. Kepler 186f, if it exists, orbiting a less violent K-type star, possibly having normal day and night. And Kepler 442b, the strongest candidate, with conditions that seem most suitable. But here's what I want you to understand. This is not a pessimistic message. This is a realistic message, and reality matters more than false hope. Because here's what we've learned on this journey. The universe is far more diverse than we ever imagined. We found real ocean planets, like LHS 1140b Dol. Even if they may not have life, they still exist. We've discovered the tidal unlocking phenomenon in the TRAPPIST-1 system, something we never thought possible. We've uncovered soot planets, dark carbon worlds our imagination never conceived. We've seen super Venuses with global volcanism, heartbeat days on Ross 128b, and environments stranger than any science fiction novel. By 2030, we'll have the technology to observe Proxima b using the Very Large Telescope with unprecedented resolution. James Webb will continue observing the TRAPPIST-1 system and give us clearer answers about their atmospheres. So the big question remains, are we alone? With a 0.5% success rate from 6,000 planets, the numbers seem grim. But remember, we estimate over 100 billion planets just in the Milky Way. 100 billion chances. And if just 0.5% of those have suitable conditions, that's still 500 million potentially viable planets. And maybe, somewhere out there, on one of our 3 final candidates, or on a planet we haven't yet discovered, something is looking up at its stars and wondering the same thing.